Hi there, I got myself another piece of rather large vintage test equipment, a Marconi TF2331 Distortion Factometer. It was sold as being in unknown condition and just for parts, but I hope it does work because it's an interesting device. So, what is this thing? From the specs, it is fundamentally an AC voltmeter with ranges from 1 mV to 30 volts in a fairly wide band from 20 Hz to 100 kHz, and yes, one can use it for that, but that's just a start. As you would guess from the name, it can measure total harmonic distortion. For that, it is limited to just the audio part from 20 Hz to 20 kHz. The distortion meter is basically a notch filter. The principle behind this is that you feed a clean sine signal from an external generator into an amplifier you want to measure and connect the TF2331 to the amp output. Then you tune the notch filter to the generator frequency and basically completely filter out the test signal. Ideally, you should now see 0 volts, but every amp will produce some intermodulations and distortions, so the result is generally not 0, and the worse the amplifier, the higher the distortion. Lastly, you can turn the signal at the input of the amplifier completely off, and the TF2331 can now be used to measure the residual noise produced by the amp. The block diagram of the voltmeter section is fairly straightforward. You can select either the input signal or an internal calibration signal to a multi-stage amplifier that at the end has a rectifier and a meter attached. A feedback loop keeps the amplifier stable. There's a switchable 400 Hz filter to suppress mains frequency hum if needed. There's also the possibility of using the voltmeter as an amp through the separate output of the amplified signal. The distortion factor meter part is more complicated, but essentially allows setting the input to a reference level and then has a complex tunable notch filter in the signal path and a selectable weighting filter for noise measurements. Of note, there's actually an RF input, and the TF2331 can directly measure noise and distortion on AM modulated audio signals on carrier frequencies from 500 kHz to 500 MHz. Also, this somewhat faint dashed line indicates that when the function is set to voltmeter, everything from input attenuator to weighting filter is completely bypassed. From the outside, my TF2331 is in relatively good shape. It has few markings on it from previous owners. The box is rather large and surprisingly heavy, probably all built from solid metal and lots of it. On the rear are interestingly 2 fuses, one marked as HT, which I think means high tension. Curious for a transistorized device. It can either be powered from mains or external 18 to 45 volts DC. I suppose you would use that for sensitive measurements when you don't want any interference, or you need to run it floating, that is, not reference to mains ground. On the other side, we have a rather corroded connector for the RF input. For a first test, I set the voltage selector to mains and connect through my current limiting light bulb. I also put a 1 volt 400 Hz AC signal on the input. Pretty much nothing. At least the light bulb stays dark, but it's more likely that a fuse is blown. I checked the fuses and they were good, so the next step is opening it up. That is quite a task in itself, as there are 6 pretty solid screws to be removed. Taking the rear off reveals only a solid metal inner frame, which explains the weight. It looks as if one should be able to push the inner frame towards the front to get it out of the outer shell. This is much easier said than done, but in the end I managed to do it. The frame is split into 3 compartments. On the right is the input section and the distortion measurement part. The smaller middle is basically just the frequency band and the function switch. There is an enormous capacitor on the right and tuned inductors for the filters along the rear wall. The PCB with the rest of the distortion meter circuit sits on the opposite wall. The most left compartment is very cramped. It has a PCB on both walls, one for the voltmeter part and one for the power supply. Then there's the instrument and range selector and an encapsulated mains transformer. I don't like how that capacitor is hanging on its leads. It's obviously a replacement, and I saw a similar arrangement and capacitor in the distortion meter section. A closer look at that large cap. It turns out to be the input capacitor of the whole instrument. Basically, the input is always AC coupled and any DC is blocked by this non-polarized 8 microfarad cap rated for 350 volts DC. Nice. The voltmeter PCB with a whole battery of large 500 microfarad electrolytic caps. And the power supply on the opposite side with that hanging cap bodged in where clearly an axial capacitor used to be. First order of business is to check the single supply voltage rail, which is minus 15 volts. I connected the plus of the meter to the chassis so it reads positive. Well, it may not look pretty, but that power supply is working. What about ripple? Well, common with many budget meters, the AN870 ranging is confused when trying to measure tiny AC voltages on top of large DC voltages. Replacing it with a trusty BM869S, which reveals that there is no ripple to speak of, so the power supply is okay, which means the reason for not working must lay elsewhere. With the power supply ruled out, I decided to use 20 volts DC input for my bench power supply instead of mains power, because it's much safer and I don't want to worry about accidentally touching live parts. And secondly, I can see the current draw and also limit the current in case I accidentally short something. So the rest of the electronics in this device does draw a current just below 50 milliamps. That low current makes it unlikely that there's a shortened cap across the supply rail somewhere, or the current would be much higher. For a deep dive, I need better access. It turns out that the mechanical construction is actually really elaborate. According to the service manual, this thing can basically fold apart. First, I have to remove that horizontal bar across the rear. But then the service manual basically just states to remove or loosen screws as needed. Right, I can see the hinges and it starts to move, but only a bit. But after removing some more screws, I got it into the fold-out state. Here's a panoramic view of the transformer, power supply PCB, front panel assembly, and the voltmeter PCB. And the instrument is still fully working in this state. Hats off to the designer. Access isn't that good in the middle compartment. The rear of the voltage meter PCB is shielded by a metal plate, and the same is true for the power supply PCB, but the distortion meter PCB shield is missing. I am sure it had one, and whoever did the hanging cap repair forgot it or did not bother to put it back in. I quickly established that the generator for the cull signal was working just fine, a nice square wave at about 2.9 kHz. I also established that when selecting voltmeter as a function, the input signal did get through to the voltmeter PCB, but using either the cull signal or input signal caused no reaction on the meter. Now highly suspicious of the meter itself, I decided to remove it for a closer inspection. It is held by a rubber ring similar to a hose pipe clamp. It should be showing 0, but it isn't. And adjusting the 0 point doesn't work properly. This meter seems to have a problem. It is supposed to be a 500 microamp meter, but when I feed 500 microamps, it just goes to mid-scale. It needs a lot more current to go further, and the needle seems to hang sometimes. I thought it might be suffering from being unused too long, and a bit of exercise will get it going. So I constructed a test rig, driving the meter with a triangle wave between 0 and 500 microamps from a function generator. I left this running for hours, hoping for gradually increased needle swings, but it stayed the same. I changed the signal generator to a rectangular wave to see if I can get it to move further by applying alternating 500 microamps and 0, but this did not change anything either. Interestingly, using the same rectangular test signal, if I shake the meter slightly, I can make it creep further to the right at 500 microamp and closer to the left at 0. Next, I took the meter further apart and gave it a good thorough dose of WD-40 on the moving parts. It seemed to go smoother now, but still not the full range. I did some macro shots of the meter to see what's wrong, like a broken spring or something, but I can't see anything amiss. If you can spot anything, please leave a comment. I said earlier that the meter is smoother now, but that's not always true. Here's a case where the meter seems seriously stuck, but eventually recovers and goes back to a smoother operation all by itself. I did not touch it at all. I have no idea why this is happening. While the meter was exercising, I connected a bench meter set to milliamps as a replacement and continued examining the voltmeter circuit because the values, while no longer zero, were not correct. Here's the main part of the voltmeter circuit diagram. As I mentioned, the Cal oscillator here was working fine, and I also traced the input signal through the emitter follower until it reached VT13. From there, some of the signal was still there, sort of, but the DC voltages were all wrong. In particular, it was impossible to set the bias such that the DC voltage at the collectors of the driver to the rectifier was the required minus 7.25 volts. I did the usual check using diode mode on the base to emitter and base to collector junctions, and all tested just fine. I also tested the electrolytic caps in the circuit and got about the right capacitance and an acceptable ESR. To cut a long story short, in the end I desoldered C69 here, one of those bright red 500 microfarad caps, because the DC voltage drops across the resistors just did not make any sense. Here's the test of this cap using again my ESR tester, this time out of circuit. This tester uses a very low AC of about 40 millivolts at 50 kHz for its magic, and I generally find it very reliable. 533 microfarad and 0.15 ohms sound about right and acceptable. But watch this. The same cap across 15 volts DC on the bench power supply set to 50 milliamps current limit. And it's a complete short circuit. I have never seen that before. A cap that tests totally fine using AC is a complete short for DC. If a cap is that leaky, you normally see indications like ridiculously high capacitance values, or the ESR tester directly reports bad or leaky cap. Here's what my replacement cap tests in the same situation. Okay, it's a lower cap value because standard values today are 470 microfarad, not 500 microfarads, but I reckon it's okay taking into account tolerances. The DC test shows just a brief blip while the cap charges, and then the current is basically zero. Okay, it was just one cap that caused the problem, but they all have the same date code of 1972, and therefore I replaced them all and readjusted the bias voltages in the voltmeter circuit, which was now possible. By the way, by removing the leaks, the total power consumption has gone down to just about 39 milliamps. For a test, I replaced the digital meter with an old analog meter that I shunted to 500 microamps. Ignore that it says volts. I'm applying an AC signal of 100 millivolts and adjusted the Cal pot to make the meter read full scale 10. Next alignment job, according to the manual, is to switch to the Cal generator and adjust its output so it aligns with the Cal mark. Now, my meter has no Cal mark, but since the Cal mark on the original meter indicates 0 dBm at 600 ohms, I can calculate that this corresponds to the values of 7.75 on my meter. The adjustment is very twitchy, but in the end this will do. Reducing the input to 10 millivolts, and after adjusting the range, the meter shows again full scale as it should. Down to 1 millivolt now. And again the voltmeter works just fine. Going the other direction, setting the range to 0.3 volts, and after setting my signal generator to 0.3 volts, I get again full scale. And the same for 1 volt. Setting the range for 3 volts and the meter shows 1/3 scale with 1 volt input, but full scale with 3 volts input. I'm quite happy that the ranging of the voltmeter works. Now for the bandwidth. I decided an easy test would be to do a quick sweep from 400 Hz to 100 kHz and watch if the meter needle changed. And I'm happy that it does not, or at least not enough to be bothered. Now to try the distortion part that I have so far completely ignored. The first job is to set the function switch to set ref level and then use the set ref level knob to set the meter to full scale. Remember, in this mode the meter is not measuring absolute values like volts but percent distortion. Then I need to set the function to reject fundamental, of which there are two settings depending on whether I want distortion up to 20 kHz or up to 100 kHz. Let's go for 100 kHz. The generator frequency is currently set to 400 Hz. After setting the correct band for 400 Hz, I can see a dip as I move the dial towards the black 40 on the scale. Now comes the slightly tricky part of tuning the notch filter as accurately as possible to suppress the maximum of the original signal and leaving only the distorted parts. Whenever possible, this involves going into a lower range on the voltmeter part, thereby increasing the sensitivity. The range setting now have a different meaning, not 1 volts, 0.3 volts, 0.1 volts and so on, but 100% distortion, 30% distortion, 10% distortion and so on. The final tuning is even more tricky because the 10-turn pot for the phase balance produces sometimes some wild fluctuations. Not sure if that's a dirty pot or inherent. I'm cutting this part short. I managed to get down to 0.1% distortion range and the meter is showing just below 4, so we have 0.04% distortion. The generator is my LAC 126, which should have less than 0.005%, but I bought this on second hand and who knows if that's still true. Further, if you recall from the specs at the beginning, the distortion by the TF2331 itself is rated as less than 0.025%, so I'm not disappointed with 0.04% for my first attempt at distortion measurement. This test was mainly to see if this rescue attempt is at all useful to continue given the state of the analog meter that has shown no signs of improvement, and I decided it is, but maybe not to go overboard. I have to accept that the original meter is probably irreparable. I think my options are try to find the exact meter, probably inside another TF2331, but these old devices are rare and who knows what condition that meter would be. So I keep this as a possibility if I happen to come across one by chance. Put in another 500 microamp analog meter. You have seen that kind of works, but that meter was way too big to fit. Also, it is rather inconvenient for the ×3 ranges. As common with AC voltmeters, the ×10 scale is 0, -20, -40 dB volts, while the ×3 scale is actually -10, -30, -50 dB volts, which means the value of 10 on the ×10 scale is 3.162 on the ×3 scale. One would have to draw a second scale, which is tricky, or use a conversion formula. Next, putting a digital meter in. This was the approach I used for the HP 3400A with its broken analog meter. In this case here, it would be relatively straightforward. Putting a 200 ohm resistor in instead of the meter would cause a voltage drop of exactly 100 millivolts at 500 microamps current. Panel meters that can read 0 to 100 millivolts are available for less than what an analog meter costs. The problem is that the voltage is floating, so the digital meter power supply must be isolated from the power of the TF2331, which means either an isolated DC to DC converter or a separate power supply. I have gone through this in the HP3400A. Lastly, I considered going all the way, adding a microcontroller with an analog input and a display of sorts, possibly with a few buttons. That could do all kinds of scaling and conversions, and if the display is fancy enough, even try recreating the look of the original analog meter. That solution also needs a separate power supply for the same reason as the digital panel meter. While it would be cool, it's quite expensive and time-consuming to make that program. Considering all this, I decided to go with a second option and get another analog meter as the most economic but admittingly uncool solution. My choice fell on the FlashStar model SD670 sold by Rapid Electronics because it was the biggest meter that I thought would just fit into the available space. And indeed, it really just fits between the cull and the power knobs with not a millimeter clearance. I do need to drill 2 holes, but that's not a problem if I ever find a better solution. I covered this before, but it's a useful skill to know, so here it goes again. The meter I bought is a 100 microamp type because I want a 0 to 10 or 0 to 100 scale. The datasheet says that it has an internal resistance of 1500 ohms. That means at full scale of 100 microamps, the meter drops 150 millivolts, simply because 1500 ohms times 100 microamps equals 150 millivolts. If you have a meter but no datasheet, simply increase the current carefully until you get full scale and then measure the voltage drop. To shunt this meter for 500 microamps, I need to put a resistor in parallel that will divert the unwanted 400 microamps around the meter. That resistor experiences the same voltage drop as the meter, so I can easily calculate the needed resistance as 150 millivolts divided by 400 microamps to get 375 ohms. 375 ohms isn't an easy resistance value to buy, therefore I decided to use a 10-turn trim pot of 1K instead. The shunt resistor is fitted and adjusted so that the meter shows full scale at 500 microamps. I glued the trim pot to the back of the meter, so if I need to, I can still adjust it from the top when the meter is installed. The new meter is installed and you can see how tight it is between the 2 knobs, but it leaves a little bit of a hole below. It does not bother me too much, but I decided to cover it with a strip of black cardboard that has some double-sided tape at the lower edge. This is how the replacement meter looks from the inside with the 1K trim pot wired between the 2 terminals. Yes, I could not leave those 2 dangling caps alone. It just upsets me. For some reason I forgot to video the one on the power supply, but here's the fix for the one on the distortion board. Looks much neater. For now I declare that repair done. There will be a part 2 because I plan to do more measurements, which I hope will be quite interesting, but for now this video is getting too long already. If you like my videos, don't forget to subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.